So let's sort of get started with a bit of background, Paul, if you don't mind. So,
not at all.
When did you start to get involved with CCS? Would you say, or CCUS, or CCU, I guess, in your case? Although,
yes. Well, it's an
what would you call what you do? Let's get to that first.
Well, if I explain how I got into it, then it'll explain. We would term ourselves CCU, but when we started back in the last century, so in the 1990s, 2000, we were looking at treating waste with cement stabilization. So it was a modification of cement stabilization solidification, but using CO2. Yeah. So back then, people weren't really worried, which is tragic. You know, it wasn't at the forefront of people's mind that if you were using CO2, it was a good thing. So as we've progressed, obviously the CO2 side of what we do has become more and more important.
Mm. But it is stored. The CO2 is stored, isn't it? I mean, it's not.
Oh,
it's
yes.
Not
it permanently captured.
Yeah. So that's pretty good. And then, so what was your sort of education or whatever that got you into that?
Well, I'm a geologist by training, and I did my PhD tramping across the Scottish Highlands, mapping Precambrian rocks.
Geologists just have such good PhD projects. I just don't get over it, really. It's not fair.
Yes, I worked in a place called the Monalea Mountains, which was, in the 3 years I did my mapping, I met 13 people. If you want solitude, it was just fantastic.
That's great. That really is good.
I did quite a lot of geochemistry alongside the mapping, and then I sort of went back to something I was interested in as an undergraduate, which is engineering geology. So I sort of retrained as an engineering geologist. And then
an engineering geologist, presumably not someone that tramps over the Scottish Highlands enjoying themselves. So it sounds like a bit of real work actually there, Paul, right?
The bit of the Monaleas that I was mapping actually contains the Foyer's hydroelectric scheme. So engineering geology was really quite appropriate because of the tunnelling that they did in the, I don't know because they put in a new pump storage scheme relatively recently. So there was a lot of use of the maps that I had made for the tunnelling. So it turns full circle. But I retrained, and then I had the opportunity to run the geomaterials master's degree that had been at Queen Mary and Westfield College. So they transferred it to us, and so I was teaching concrete and cement and aggregates and stuff.
Sorry, where was that you were teaching?
At the University of Greenwich.
Greenwich, right? Yeah.
So it had NERC grants for the masters in those days, but then when the grants finished for master's degrees, Greenwich weren't terribly keen on keeping on the master's program, so it all folded, which was a shame. But it meant that Colin Hills joined us from Imperial, and he brought with him his contaminated land expertise. So it was through him and through the treatment of contaminated land using cement and CO2 that we got into treating waste with CO2, and then decided to form the company in 2006.
2006, right? That's a long time ago, isn't it?
It is, yes.
Yeah, things come and go. Oh well, and I mean, do you think now is like the most sort of promising time you've seen, or were you more excited earlier on?
Oh, definitely the most promising at the moment. And as you'll hear in my presentation, now is the time to be in carbonation and mineralisation, because the big investors are very keen on investing at the moment. So you've seen quite a lot of investments in companies that are are doing carbonation and mineralisation.
Okay, well, that's very good. Well, that's a good lead into your talk. So please let's hear about carbonation.
Right, here we go then.
Thank you.
Right, just check that that's all right.
Yep, I can see that.
Excellent. Right, so I want to talk about mineralisation and carbonation in general as a CCU technology, and then finally talk about what Carbon8 Systems is doing. As it shows there, I'm the technical director of Carbon8 Systems nowadays. I did form the company alongside Colin Hills in 2006, but we've come a long way since then. So first of all, what is carbonation and mineralisation? It's the reaction of calcium and magnesium, and sometimes iron, oxides, hydroxides and silicates with carbon dioxide, and you form carbonate. So in a very simple form, calcium oxide plus CO2 gives you calcium carbonate. On the right-hand side of the slide here, you can see two scanning electron microscope images, which were really my colleague Colin Hills's eureka moment. He was working on cement stabilization of wastes, and this is a particularly difficult waste contaminated with lead, nickel and zinc, and he was trying to solidify it with cement. So you can see these bright grains here are grains of calcium silicate in the cement. And it sat on his desk as a sludge for months, and he didn't understand why it wasn't going hard, or else the poisoning of the hydration by particularly nickel and zinc was occurring. So, but he noticed as he took it to the SEM that it was getting a coating, a white coating on it. And he thought, oh, what happens if I expose it to CO2? And this is what happens. The calcium silicate you see here has a darker rim. And on exposure to CO2, the calcium is sucked out of the silicate and redeposited as this paler grey material in the matrix. And you can just see these little needles. And if you look at it on a fractured surface, you can see all these calcium carbonate needles. And as soon as he had exposed it to CO2, those needles lock together and you get a stabilized, solidified mass. So that was his eureka moment. And from that, we've been working hard to develop the technology. So those sorts of calcium and magnesium compounds can be found in a whole variety of basic and ultra basic rocks. So basalts and dunites or olivines and serpentinites. But also, which is of more interest to us, is the alkaline industrial residues. So things like steel slags, air pollution control residues, which are where you inject lime into the flue gas to capture the acidic gases, chlorides and sulfates and things. Cement residues or crushed concrete, amongst others. So there are two principal environments for carbonation that you might see written about. First of all, there's a wet form where you have a high water to solids ratio, and generally speaking, you get precipitation of carbonates from solution. So you tend to get nice pure carbonates forming, sometimes known as PCC, and has been particularly well recognized within the ETS as a potential for actually allowing permanent capture of carbon dioxide and fitting in the ETS scheme. The other type of carbonation is what we do, which is a dry carbonation, although you need the water to allow the CO2 to ionize in order to react with a solid. You can't really react a gas with a solid very easily. But we have water solid ratios down below 1. Carbonation will occur naturally, and it's part of the weathering of rock. So it comes back to my geological background. Or if you leave alkaline residues out in the atmosphere, they will eventually hydrate and carbonate. But because of the low concentrations of CO2 in the atmosphere, it takes years for it to happen. So what we're interested in is accelerated carbonation, and you change the conditions of the reaction. And there are lots of different academic work going on different ways of carbonating, from using supercritical CO2 through high temperatures and pressures to, again, what we do, which is try and manage the carbonation reaction at atmospheric temperatures and pressures. And we can achieve reaction rates that go to near completion in 10 to 15 minutes. Whoops. Okay, so what are the advantages of carbonation? First of all, you can get permanent capture of the CO2. So if you form the calcium carbonate, it's there, and unless you put it in high temperatures above 400 or 500 degrees, it will stay there. And you can get rid of it if you put it in acid conditions. So you do have to think about acid groundwater or acid conditions. Very importantly, though, it's an exothermic process. So when you form the calcium carbonate, it actually releases energy, usually in terms of temperature. And so it's one of those reactions of CO2 that you don't need to put in a lot of energy to enable the transformation. So you're not reliant on having renewable energy sources to make your products carbon negative. And we can also use very low concentrations of CO2, so from flue gas directly, so at concentrations below 20% down to 10%, without any need for purification. So there are large quantities of reactive material, both the natural rocks and ones formed as residues from, I said, anthropogenic activity. So here's a sort of diagram of them, and the potential of capturing more than 1 gigaton of CO2 per year globally in industrial residues. And this is a summary of what we think each of the different industries, if you treated all their wastes, the sort of level of CO2 capture that you could manage. You have to bear in mind, though, that there are other uses for some of the residues. So carbonation isn't the exclusive way they would be managed. So coal, I've done it again. Coal PFA, for example, it's a diminishing resource and it's very much used in cement. So there's not that much available, and particularly of the right composition for carbonation. But according to the GCI, the Global Carbon Institute, their roadmap in 2016, they looked at carbonation and particularly potential CO2 utilization, aggregates and concrete, and you can see that they considered that there was huge potential for storing this or capturing the CO2. So by 2030, 3.6 gigatons in aggregates and 1.4 gigatons in concrete if we get the strategic actions right. I look at the figure for 2020 and wonder whether we did achieve 100 million tons, and I don't think we did. So I don't think we've got quite the right strategic actions implemented yet. So we'll come back to that later on. But the other important thing about it is concrete and aggregates in terms of potential annual revenue. Again, very good market for these materials, even though overall you would say they were low value. Because of the volumes involved, they can actually generate a lot of income. Oops. So who's doing what in 2021? And where are the main excitements, if you like, in carbonation? If we look at the carbonation of natural materials, so these basalts and olivines or serpentinites, the first one to think of is the people in Iceland, Carbfix, who have hit the news fairly recently because they're using both CO2 from the geothermal plants in Iceland and also now looking at the direct air capture. I'll come back to them in a second. We've also got enhanced natural weathering. Again, the University of Oxford have just obtained a large amount of grant funding to spread mine tailings on fields and let them naturally weather to absorb CO2 from the atmosphere. There is a company called Green Sand who are selling crushed olivine as a garden growing medium. So you can see the bag there, olivine sand. And they're also spreading it on beaches or using it in paths or along railway tracks. So crushing it so that it will absorb CO2 from the atmosphere. We're also using natural materials, natural minerals for other carbonation processes. We've got serpentinites where people are extracting the magnesium oxide and then manufacturing magnesium-based cements, which are carbonated to form the blocks, for example, Cambridge carbonates. And another Dutch company, Green Minerals, is making paper from the carbonation of olivines. So we talk about notable current activity. Oops, we're going through too quick. And by notable current activity, I'm thinking really about publicity and PR that these companies are raising, and also the investment. So many of these companies that I'm talking about here have recently had significant investment from both strategic venture capital companies and straightforward venture capital companies. So Carboncure, probably the most famous company doing carbonation. They introduce pure CO2 into fresh concrete as it's poured, and that accelerates the hydration of the cement and thereby reducing the amount of cement required, and also reducing loads and flows of traffic. So they argue that they can save more than 45,000 tons of CO2 a year. I mean, they've had more than 1 million truckloads of concrete, according to their website. But they actually use very little CO2 actually in the concrete. It's about 1 kilo of CO2 per ton. But because it's nucleating the hydrates, the concrete goes off quicker, and therefore you need less cement because you're getting the same strength. So the CO2 saving is based on the reduction of the cement, and because you get faster setting, there's a time saving as well. They also manufacture precast blocks in the same way, so they go off harder than normal concrete. Then there's Solidia again in North America, and a little activity in Europe. And they're manufacturing a special cement that hardens through carbonation rather than hydration. So it can be manufactured in normal cement kilns, but it requires much lower temperatures. So you're reducing the emissions from the fuel consumption. The cement is based on a mineral called wollastonite, which is a calcium silicate, which reacts readily with CO2 in the presence of water. And the concrete blocks are made with cement, are then cured in a chamber of CO2 for 24 hours rather than the 24 days that you might take if it was normal hydration. They argue that they can capture about half a ton of CO2, a quarter of a ton of CO2 per ton of concrete. So eliminating, I can't quite understand why they say they eliminate tons of concrete going to landfill. I haven't worked that one out, but they think they can capture in the order of 1.5 gigatons of CO2 per year by replacing normal cement in concretes. So if we move on to what Carbon8 Systems does, it's looking at these industrial residues, so alkaline residues. And there are a range of those, some that are illustrated here. And you can see the average percentage CO2 uptake of these residues. The highest will be steel slags and cement kiln dust, which you can get up to 25 or 30% by weight of CO2 into some of these, particularly stainless steel slags, the EAF or AOD slags. Paper ash is another good one because paper has a lot of calcium silicates in it, kaolinite, for example, and when you burn it in the recycling process, it makes a very nice reactive material. And then the area that we're concentrating on mostly at the moment is in the residues from cement manufacture. But there are another industrial residue would be mine tailings, the ultrabasic and basic rocks from mining things like nickel or chrome. But if you look at the carbonation of industrial residues, the amounts that are involved, I've got some global volumes there that sort of match the ones I had earlier, but we've concentrated more on Europe. And if you look at the average uptake for some of these residues, you can see that there's the potential to capture about 28 million tons of CO2 in those five residues. But more importantly, you know, it's income generation. You can save the cost of disposal. So you're looking at a market of over £12 million within Europe. So going back to mining residues, and another company that's been making a lot of noise recently, Mineral Carbonation International, which is based in Australia. And in contrast to some of the others we've talked about, they have a wet carbonation process. So currently they're only really at pilot plant level, I believe, processing just a few hundred tons of CO2, but they've got grand ideas, planning a demonstration plant. I think they're probably under construction to process around 50,000 tons of CO2, and then a full plant which converts 1 million tons of CO2 is on the drawing board, they say. And at the moment they're concentrating on the carbonation of nickel mining residues, but are talking about using other industrial residues within their demonstration plant. Nickel tailings are serpentinite based, so again they're using the magnesium carbonate that is produced to make either blocks or plasterboards, which is quite interesting. I love their website though. They say that their technology is developed under research commercial secrecy, and I think it's something that we all have to watch out for, that we don't tell everybody about too much about what we're doing. But they've been going for quite a long time and have spent a lot of time developing their plant, so it is quite interesting. But it's very difficult to find out what they're doing because of this commercial secrecy. They say that by 2040, using their technology, they could lock away over 1 billion tons or 1 gigaton of CO2 into building materials. So interesting to see how they're getting on. Another residue, steel slags, Orbix or Carbstone, has been going for quite a long time and are doing a variety of things with steel slags. They pay for their process very much by recovering the residual metals in the slags. So they grind the slags and then recover the metals, and then originally they were pressing the material into blocks and carbonating in an autoclave, so using higher temperatures and pressures. But they also market other fine-grained materials or granular materials that I think are made in a process fairly similar to ours, where you pelletize the fine-grained residues in an atmosphere of carbon dioxide. They're also making a fine-grained material called Carbinox, which they sell as with the label that it's able to absorb CO2 from the air at a later date. Not clear whether they're using flue gas derived CO2 from the steel plants where they're based, but I suspect if they're using an autoclave, they're probably using pure CO2. A very similar technology will be in Carboncure in Canada. They're again making precast blocks from steel slags cured in CO2. They're of interest because they're part of the X Prize. So there are, I think there are 6 companies left in the X Prize, of which 2 or 3 are carbonation companies. The construction and demolition waste is another interesting area of carbonation. The cement industry is responsible for up to 7% of the 8% of the global CO2 emissions, and they're working hard to reduce their image at least, or become net zero by 2050. And the Global Cement Association has a 6-point plan, of which really we can think of 3 of them as being related to carbonation. So again, there's a big move by the cement industry to look again at carbonation and see what it can offer them. So one is the use of supplementary cementitious materials within the cement clinker, because there's now a shortage of PFA, which, as I said before, had been commonly used in cement. As that's reducing, they're trying to find something else which will reduce the amount of CO2 high cement clinker. And they're also looking at various ways in which we can reprocess construction and demolition waste as an aggregate, and also as other things for use in cements and concrete. And very ironically, they talk about enhancing the carbonation of concrete. The carbonation of concrete has always been considered by structural engineers as a real problem, because if you carbonate the concrete, you end up reducing the pH of the concrete and therefore reducing the protection of the steel. So if you have a steel reinforcement in the concrete and it carbonates, eventually the steel will corrode and the concrete will split. So carbonation of concrete had always been thought of as a bad thing, but now it's a good thing because it's capturing the carbon dioxide back from the air. But there's an interesting concept of urban quarries. If you think of an old concrete building as a potential to quarry for aggregate and to capture CO2, then it's quite a large source of material. The concrete itself will carbonate only very slowly, depending on the quality of the concrete. So if you crush construction and demolition waste, it will contain quite a lot of uncarbonated cement paste. And there are people like Blue Planet in the US, again, another company that's just received quite a lot of investment, which, like ourselves, is manufacturing an aggregate. They say from a variety of industrial waste, but they seem to be concentrating at the moment on construction and demolition waste. So they crush the concrete and remove the cement paste from the other aggregate in the concrete, so the sand and gravel, which they then sell on and into the market. They then dissolve CO2 in a sort of water, brine, ammonium salt solution and grow calcium carbonate on fine silica seeds. So it's very much a water-based capture, wet carbonation, and you get precipitation in these sort of ooid forms. Going back to my geology, you get concentric growths of carbonate on a silica core. The economics depend on the value from the sand and the gravel, and also on the value of the CO2 that they're capturing. They've got so far as having a pilot project, and they've used their aggregate famously at San Francisco Airport. But it's always difficult when you're in America thinking about how much CO2 they're actually capturing. So I tried to work it out, and they were talking about 477 kilos of CO2 per ton of concrete, which I think is a bit high, and there's something not quite right in the maths there. There's the lovely phrase on their website about calcium carbonate capturing 44% CO2. Well, yes, that's the molecular weight of the CO2 in the carbonate molecule. So interesting. So carrying on with construction and demolition waste, several projects use C&D waste to make these supplementary cementitious materials. And as I say, it's partly driven by the reduction in availability of PFA. But what they're doing is carbonating the calcium silicates in the cement, which produces the calcium carbonate sort of filler, replacing what would be a limestone filler in the cement, and also a silica phase. So if you recall that first SEM image of this calcium silicate, where the edge of the silicate is devoid of, the calcium has been sucked out of it, that makes an interesting material that can be, seems to be of value as a what's called a pozzolan. So adds to the longer term strength development of the concrete or the cement. The problem with construction demolition waste, as far as I'm concerned, is it's a very variable material, depending on the age of the building, the age of, and the level of exposure of any part of the building. So, and also from our point of view, in the UK, 95% of C&D waste is already recycled, so it's sold back into the market as general fill. So where we come from is about treating residues that would otherwise go to landfill at costs of up to £120 a tonne. So our business model is based on the fact that we're avoiding this landfill cost. A lot of the residues, as I said, can react with up to 30% of CO2 by weight, and you get that permanent capture, and you then can manufacture a product with some value. As I say, it's a low value, high volume market. And if you treated all the residues that were available, you're not really impacting on the overall use of aggregate and the aggregate market. So we're looking at typical treatment costs of around £25 to £30 a tonne. So you can see for some residues, the owner of the residue are going to be saving £90 a tonne in disposal costs. So it's a very much a wealth creation technology for those waste producers. And if they can get value out of the CO2 captured as well, then it's a very profitable business. And you can think of capturing the CO2 potentially directly from their flue gas, and the cost of capturing that CO2 is no longer a cost. It's actually a saving, and it can be a saving of up to £200 a tonne. So our Carbon8 Systems has currently two propositions. The one we've been marketing most intensely at the moment is our containerized system, carbon capture in a box. And we've had two commercial demonstrators in Ontario and also in the UK at the Ketton Cement Works. And we've just installing our first fully commercial license with the VCAG group at their cement plant in Montpellier in France. Important thing about this scheme is that it's modular, flexible and scalable. And as we like to say, plug and play. So it's commercially viable for smaller sites. And the nice thing is that you're capturing the CO2 directly from the flue stack of, for example, the cement works. But our technology has been proven already at commercial scale. We licensed the technology to another company in 2010, and they've built 3 fully commercial scale plants in the UK that are treating air pollution control residues. So the fly ashes, lime-based residues from energy from waste. They have the advantage that they can utilize larger volumes of CO2 because the throughput is greater, but those commercial plants at the moment are using pure bottled CO2, which comes in a tanker at up to £100 a tonne. So it's it's an expensive commodity to use the CO2. But if you've got large waste producers, then a centralized site like that is more economic. But you can think of it as lots of containers lined up without the containers around them. So it's all built on the idea of modular plant. So this is the VCAT cement works. It's always nice to see it in the sunshine. The last time we were there, it was covered in snow as well. As I said, the containerized system has been proven through 2 pilots, first in Canada and then in the UK. And we moved these containers down to VCAT in the latter half of last year. We have been unfortunately hit by the problems with travel with the COVID crisis, and we haven't fully commissioned the plant yet. At the moment, VCAT are on a 5-week maintenance. So when we can get back there to finish the commissioning is still in doubt, but hopefully by the end of March, we'll be able to get back. So this is the plant in Ontario, where we made some 50, 60 tons of material from the cement residues from the CRH plant. And here you can see the flue stack above the container, the big grey pipe, and in front of it there are 2 smaller blue pipes, which are the in and out from the flue stack. So all we do is take a bypass of the gas, pass it through our mixer, strip out some of the CO2 and return the spent flue gas back to the flue stack. So there are no emissions, and we are using probably about 50% of the CO2 in the flue gas. It all depends on the rate of flow and the time that we allow the reaction to continue. So you can see here a graph of CO2 in and out. You can see the in is around 10% by weight of CO2, and at the maximum reaction time, we strip about 50% of that down, so down to 5% concentration. But very soon, you're diminishing returns, so there's no point in keeping the material in the batch for any longer, because the extra amount of CO2 you're stripping diminishes very rapidly as you get to 30 minutes. In that pilot, we made some nice aggregate there on the left-hand side, and it went into both concrete blocks. And we also experimented with making a fertilizer. These cement residues are high in potassium, so they make a good fertilizer. And because you're carbonating it, the release of the alkalinity is moderated. It's got a good buffering capacity. So we think there are a lot of advantages of using it as a fertilizer. What would be interesting to know is how much of the CO2 is then trapped in the soil rather than released again. So our last demonstration was actually at an energy from waste plant in the Netherlands, and we did the demonstration using fly ash from the energy from waste plant, where again they've got disposal costs in excess of 120 euros per tonne, and the aggregate is currently being tested in a local block plant. Unusually there for us now, we used pure CO2. It's an interesting case there because the AVR Energy from waste plant already captures and purifies some of its CO2, but it's used in greenhouses. So during the winter, when the greenhouses have got their own heat, they use their own CO2. So they were looking for other uses of the CO2 that they were already producing. Fly ash is not particularly reactive to CO2. So in this case, it's very much the business model is about treating a waste that would be expensive to dispose of rather than capturing large amounts of CO2. I just put this slide up for interest's sake. This is the sort of variety of residues that we've looked at in our lab and the products that we can make from them. But I should emphasize that we're not really completely obsessed with making aggregate. We think, like everybody else, that we can make some quite exciting materials with higher value from a carbonation process. So in summary, carbonation mineralisation generating a lot of interest at the moment from the cement companies, steel companies, and from investors. And I believe there is the potential to capture gigaton levels of CO2 in a value generating process. So you can make money out of capturing the CO2 rather than it costing you a lot of money. Most of the activity are generating products for the construction industry, but we believe you can make higher value products. We've got drivers for the growth in the market for the low carbon buildings. So lots of people want to have low carbon buildings. So that's encouraging us to carry on with the work we're doing. But we need to have better CO2 footprint labeling, looking at whole life assessments and looking at driving public procurement to use these low carbon materials. It would be nice to have value on the CO2 in the way of tax incentives, etc. And from our point of view, we need incentives to recover waste and process waste materials, particularly existing waste piles, which are an untapped resource. We need to promote the circular economy so that these wastes are recovered. And I think that's me. Thank you very much. Please, I'm hoping I'll get some questions.
Thanks very much, Paula. Let's see if there's any questions come through in the chat. Yes, a question from Kevin, I guess. Kevin Dale. You want to ask your question, Kevin?
Well, I'm sure you can read it out for me, but okay, yeah. I was saying presumably to go out and specially mine basic igneous rocks like olivines and things to transport them in trucks and crush them into pellets or whatever, it's going to involve a huge amount of CO2 in that process. So I guess that's why people are turning to mining residue and such like. But I was quite worried that it should be too carbon intensive sometimes when you were speaking at the beginning of the talk there.
Absolutely, and that's one of the reasons why we haven't looked at serpentinites and things very much at all. I mean, if you take the example of the British Isles, you wouldn't want to be digging up the Lizard or Shetland Isles. They're certainly nowhere near the sources of CO2, and they are the most beautiful parts of the country, so it wouldn't work in the UK. But there are some large deposits of serpentinite around which are exploited for their mineral resources. So you're digging them up anyway, and you get the mine tailings. So they are definitely worth looking at. The big problem is the grinding and crushing, and serpentinites themselves need a lot of pre-processing before they will really carbonate well.
Thanks,
so I'm not convinced.
Thank you.
Okay, Peter Ame. By the way, could you introduce yourself when you ask your question as well, please?
Okay, I am Peter. I'm a PhD researcher with the University of Edinburgh. Thank you, Carey, for the presentation. It really got me interested. I'm thinking with the push for net zero emission, utilization of carbon, it's a good way to go. At least it creates an added incentive to push people to really want to put some effort in that direction. But I'm interested in the phase of CO2, since you've worked in the lab, and I don't know if you'd have any thoughts on the phase of CO2 that's more reactive or more useful in carbonation in terms of rate. Because earlier you spoke about gaseous CO2 rates not being fast enough to be economically viable for carbonation, sort of.
Yes, I think I wouldn't agree. We use gaseous CO2 at atmospheric temperatures and pressures, and we have a commercially proven process. So I don't think there is a need to go to high temperatures and pressures or supercritical CO2. I think you're adding so much complexity to the processing, the engineering of the process, that you soon make it uneconomic. And I think it's interesting to see that a lot of that work is still within the laboratory at universities. It hasn't developed as commercial processes. So I think our philosophy as a company has to be always keep the engineering as simple as possible. So we use traditional cement type mixers and conveyors, and you don't need to necessarily even have high sealing. You don't have to have the mixers particularly well sealed, because you can drive the CO2 through from a flue gas, or if you're using pure CO2, you use up what you inject, so it doesn't escape. So yes, I believe that normal gaseous CO2 is the best. We have experimented with I have dry ice, and we got a bit of a shock because the reaction went off so quickly, and it was almost explosive. So we didn't play with that again much.
Okay.
Any idea why it was so fast, Paula?
Well, it's this phenomenon, well, I can't say that word, property of CO2, that it dissolves in water at a lower temperature better. So the solubility increases with decreasing temperature. So if you have it very cold, it will dissolve in the water much more efficiently and transfer into ions and then diffuse into the solid. So I think that's why dry ice works so much more quickly.
So you think that the solubilization stage is maybe the rate limiting? Yes,
so definitely, yes. You can do a very simple experiment. If you take cement and you wet it and then add CO2 to it in a bottle, you can see how the CO2 is absorbed into the cement. So normally you would do that at a moisture content of about 10%. As soon as you get up to 20 or 30%, you can see how the reaction has slows down completely, almost to a stop. So yes, what you need to get efficient reaction is a very thin layer of water around your grain, so that the CO2 can diffuse to the solid very quickly.
Interesting. Herbert, a question or a comment?
Gee, you know me very well, John. Comment.
So maybe some people hear that and come across yet.
I just wanted to say, Paula, I thought that was a very nice and interesting seminar, but where can we read more about it? Is there some literature that would sort of go in parallel with what you were saying? Oh,
definitely, yes. Colin and I have just published a paper in Frontiers of Environmental Energy.
We'll put a link to it on the.
Yes, I can send you the link. Yes, which is very much similar to the seminar I've just given, which outlines the different forms of carbonation. It particularly uses our geological background by thinking, well, no, we've got a Faraday paper coming out shortly as well, which will have the same sort of content, but put it in a geological context. So yes, and we, as a company as well, Colin and I have published quite widely on our progress as a company in developing the commercial. So you can find papers in waste management or in the published proceedings of the Accelerated Carbonation annual meeting, ACME, I think it's called.
But do you think that Frontiers and something or other and the Faraday paper are the best?
Yes.
If you somehow send through explicit,
I'll send it on so he
that
can
would be nice.
Yes.
Thank you very much. It was a nice talk.
Thank you very much.
Sorry. Derek,
okay. Yes.
Can you introduce yourself, please?
Okay. Good afternoon. My name is Derek Odundri. I'm a PhD candidate at the University of Southampton National Oceanographic Center, and I'm working on basalt samples. And your presentation really kept handy.
Okay.
Yeah. So I'm also looking at mineral carbonation as well. And in your presentation, you talked about the cap fix process in Ireland, where CO2 was used to react with carbonic acid with water to form carbonic acid, and the carbonic acids reacted to form a dissolution and later on a precipitation reaction.
Yes.
My question is, now during the dissolution stages, we know minerals in our basalt samples, the likes of the pyroxene, the plagoclase, the olivine, and say the volcanic glass will react, form the precipitation to form stable calcite, magnesite, and siderite.
Yes.
Now, which are the prominent or are the abundant minerals during the dissolution stage that will form these carbonates in the pores of the basalts? What should we look out for? For example, I'm working on thin sections right now and I'm looking at the mineralogy which are more abundant in forming carbonate rocks. We've got clay, we've got clays, we've got olivine, we've got
well, I'm sorry, I'm not a particular expert on the carbonation of basalts. From the literature, I would have said that the olivines and pyroxenes, and geologically, they would be the less stable. I always think about the stability that I think it was, it's going back to my geological degree, which is a bit of a long time ago. You have a stability series. So olivine is the least stable because it's formed at the highest temperatures and pressures in the Earth's crust. So if you bring it up to the surface, it's the less stable. So it will be the most reactive. And it also has a higher proportion of magnesium and iron in it. So you'll get the magnesium and iron out of it much more readily than if you're trying to react to pyroxene, which is lower down in the reaction series. Oh, I nearly got the name then. Bowen's reaction series.
Yeah, very correct.
Yes.
Very correct.
So I would, and generally speaking, people are concentrating on carbonating the serpentinites and olivine derived rocks.
Yes.
Basalts I see as much more problematic because they're not as, they're more stable basically than those ultra basic rocks. So good luck with your PhD.
Yes, thank you.
Very interesting.
Yeah, I think basalts, just because of their reactive natures compared to siliciclastic rocks, which are not reactive, and with basalts, if there is a carbonation reaction, then we can be confident that there is not going to be an upflow of CO2 up deep the structures in our reservoirs. So that's why.
I think it's a brilliant idea about pumping the carbonated water down into the basalt formations. I think the map of all the basalts in the world doesn't really give you a good indication of where it's actually possible, but there is an awful lot of basalt around. So, but again, the basalt tends not to be where the industry is, where the CO2 is. So you have to then resort to air capture.
Yes, that is the problem. But for the siliciclastics, yes, we are also very scared of, there is a lot of monitoring that has to go with it because CO2 is pumped in deep the structures, and obviously due to fracking, they might go up deep the structures, and we don't want to continue the same process again. But yes, like
you've got to be very careful about expansion of the cracks and things when you form the carbonate. Yes.
True. But as you alluded, the basalts are in the mid-oceanic bridges. They are far away from the industry, so that's
and they're underwater.
Yeah, so that's a different challenge. Thank you.
Okay, can we just get some more questions in? Amelia Mitchell, could you ask a question? Introduce yourself quickly, please.
Hi there, Amelia at Element Energy, low carbon consultancy in the UK. Firstly, great presentation, Paula. You're very much making me miss my geology field trips. Looking forward to reading those papers. On a less scientific note, you mentioned the economic drivers being avoidance of waste disposal fees.
Yes.
I was wondering if there's particular countries or regions where these fees are large and where you see the company expanding into as a kind of technology deployment market potential area aspect.
Absolutely. Obviously, that was part of our main market research early on. And even if you look across Europe, there are big differences in landfill costs. And if you take, I was going to say 28 countries, you can only take 27 nowadays, can't you? Across the 27 countries of Europe, only about 12 of them have substantial landfill disposal costs. They tend to be the northern states, so Nordic and Benelux countries, Germany, Netherlands, Belgium, France. But once you get more southerly and easterly, the landfill tax goes down considerably. It's a shame, you know, you think about the European community all being the same, but the implementation of a lot of these waste directives and things are based on in-country legislation. So the likes of Italy or Spain don't have as high landfill tax at the moment as the Northern European countries. The UK is very good. It has a high landfill tax, so the cost of disposal of these sorts of residues in the UK is quite high.
And have you looked anywhere sort of outside of Europe, for example, Australia or?
Yes, it's much more difficult to get detailed information, but generally speaking, if you take big countries, they consider that they have a lot of space. And even though you think of them as being clean countries, like Canada, for example, you would think Canada is, oh, they're nice clean. They think of contamination and industrial, but actually they have a lot of landfill and it's relatively cheap. Similarly, in America, a lot of things go to landfill in the States where we wouldn't be landfilling them in the UK because they have so much more space. It's actually similar in Germany, although the costs are higher. There's a lot of landfill in Germany, partly because of the legacy of East Germany and a lot of quarries and mines in East Germany. So there's a lot of holes to fill in. So it's a very interesting topic, looking at waste disposal across the world.
Brilliant, thank you. Very interesting.
Haroon had a question, I think.
Good afternoon, Paula. Just a quick question. I missed this. Are you a commercial operation at the moment? And also, if so, have you started making any profit?
That's a good question. The company that we licensed the technology to in 2010, so have 3 fully commercial plants operating. As far as I know, they're making a good profit. It is a profitable business. We, as a company ourselves, at the moment are not making a profit. Particularly at the moment, we're in a major development stage, and we're actually looking for around a investment. So we want to expand, and we've got a big pipeline of opportunities that we need to expand to service. So it's a really exciting time for us.
So your funding is coming through licensing revenues?
Yes, predominantly what we like to do is effectively sell a company the boxes and then run them under license. So they operate, but we monitor them. If all being well, in the next few weeks, we should have live feeds from our container in VCAT so that we can constantly monitor what's happening. And that's the idea on the longer term, that the companies will license us to manage their facilities remotely.
Good luck.
Thank you. Thank you.
Andy Limbrick. Sorry if I missed you earlier.
Hello.
Hi, Paula. Very interesting talk. Thank you very much. I'm from Greenland Reclamation is my company.
Mm-hmm.
Also trained as an engineer and geologist, so
Excellent.
very interested in your talk. My question is around the regulation of the products, or the aggregates that you're producing. So, I mean, we've been involved in discussions with the Environment Agency for decades over the status of the use of coal ash in construction. And the regulators take a very conservative approach to its use, even though, you know, it's been used in motorway embankments since the early 60s or late 50s. So I was wondering if you've bumped into that at all, and whether the regulators will accept the aggregates as a product, or whether they still want to regulate their use as though they were a waste.
Yes, it's a big problem across the world, in that everybody has a different way of looking at these things, again, even through the same legislation. In the UK, the 3 commercial plants have an agreed end of waste position with the Environment Agency. So the aggregate is a product when it leaves the site, on the condition that it is used in concrete. So it principally goes into concrete blocks.
Okay.
And it has end of waste status for that. And that's the basis that we operate on, that the aggregate has to meet the specification that we set for that end of waste. Yeah. Across Europe, it's much more difficult. Each country has a different regulation, and it's difficult to see which specifications that apply to an aggregate such as ours. So yes, it is an issue. But with the increased emphasis on the circular economy and using waste, then I think this issue needs to be examined much more. We base all our work on the idea of the risk and stopping the pathway. So if you use our aggregate in a bound application, with the extra security of the cement and concrete around it, then we think that the risk is very low. And we maintain a specification for the aggregate because of that.
Great, thank you very much. Well done for getting agreement on that.
I mean, some of in a way, the air pollution control residues for which the end of waste is agreed is one of the worst types of residues that we've been looking at. So some of the things like cement residues are already spread on the land in many countries. So the use of those and as an aggregate is fairly, I'm fairly confident that that's environmentally sound. And paper ash, for example, has very little contamination in it. So again, it's a very good aggregate. So it does very much depend on the waste stream that you're looking at. And we're fortunate that we did start off with the worst, if you like, the APCR.
Thank you.
Okay. Well, thanks very much, Paul. Unless anybody's got any more questions, I think
if Genevieve is still on the line, I think we had a question from Genevieve, but she might have
gone now.
Oh, I'm still here.
Hello.
Thank you very much for that presentation. It was fantastic. I was wondering about, you mentioned that these materials are alkaline. Do you think they've got any potential for use when it comes to things like ocean liming, whether that be directly or through application to land and then traveling through the watercourse?
Well, that is very much the approach of the Oxford group and the enhanced weathering. So the idea is that they spread the basalt on the land, and it gradually, the ions gradually go into the ocean. and are for ameliorating the acidification of the oceans. I'm afraid I wasn't convinced by it, and I had a very interesting conversation with them at the time at the Sackler meeting, but it's an interesting concept. I think it's quite a complicated one. There is the potential for doing that, yes.
Yeah, it is. I'd agree with that. I was just wondering if you had any thoughts specifically
Well,
where more it comes from waste would be something that I would be
I
curious about.
Yes, I wouldn't be spreading too many of our wastes on because I do think you have to have them in a controlled environment, and you want to be able to recycle them in a sound way. And that was one of the things I didn't like about the idea of spreading rock. I know we've just talked about how the basalt will carbonate, but in carbonation, it's going to be releasing some of the other heavy metals that is contained within the basalts. The basalts aren't pure, magnesium and calcium and iron silicates. They've got trace elements in them, and those will be landing up in the soil as well. So I don't like the idea of spreading wastes. And in that case, I might count the basalt as being waste as well. And that's where I had the rather vociferous discussion with the people from Oxford.
Yeah, it's definitely an interesting thing to think about. I was actually, I was very curious about the kind of the concept of the wet methodologies where they, you said you get a much purer material out the end. That's the type of thing that makes me think maybe if you're going to be putting things to land, maybe it should be that type of stuff rather than.
Well, the reason you get purer calcium carbonate there is because you're leaving the residue behind, and you're dissolving the carbonate ions in the water to reprecipitate them, dissolving the calcium ions in the water, and then they react with the carbonate ions from the CO2, and you get clean precipitate of calcium carbonate. So you're separating the residues from the final calcium carbonate product. And where that is particularly valuable is those pure calcium carbonates could be used as fillers and all sorts of things. So much higher value product, but you have to dry it and all those sorts of things, make it more complicated.
True. Thank you very much. That was really helpful.
Thank you.
Okay. The last question from Peter.
Peter from Edinburgh, and thanks again for the opportunity. Yeah, quickly just to say, as a follow-up to what you said, what I asked earlier about the phase of CO2, I currently work on CO2 storage, and I'm looking at the phases of CO2 that could be stored. And I find that in the literature, lots of work have been done, and especially using supercritical CO2. So the reason for that is that injection of CO2 into saline reservoirs is mostly done as supercritical. So I was just thinking probably it hasn't been considered in carbonation yet to look at the effect of phase on mineralization of CO2 and minerals in rocks.
There has been quite a lot of work done with supercritical CO2 and carbonation, and you get some good results. But the problem, as far as I can see, is the energy required to get the CO2 into the supercritical state, and then controlling the process, having a reaction chamber that's economic. And so developing it into a commercial process, I think, is difficult. I mean, I think that's one of the big problems with carbon. So first of all, I have to say that I don't think we can solve problems of CO2 without carbon capture and storage. We have to be able to capture large quantities of CO2 and store it in the geological environment. But the big problem with it is transporting the CO2 and having to liquefy the CO2 to do that transport. That's where, as far as I can see, quite a lot of the cost comes in. So if you're going to use supercritical, you're doubling that problem.
Okay. A quick final one. In dry rocks, have you tried CO2 on dry rocks? And must the rocks be partially saturated at least to get a reaction, a carbonation?
Yeah, I think if you're trying to react a gas and a solid, you do need the moisture as the catalyst, if you like.
Okay, thank you very much.
John, can I just make one comment?
Yeah, go ahead, Herbert. Can I stop you, Herbert?
Is that a can or a may?
Get on with it. Come on.
I just wanted to say, Paula, your statement just a minute ago, you can't see how we could really progress properly without carbon capture and storage, I believe to be totally correct and also quite obvious. How come so many people, and even people of important situations, don't see it?
I don't know. I think it's just the volumes of CO2 that are involved, and you know, we're not going to stop people making cement or steel. They're, you know, fundamental to our way of life, and so we're going to be generating the CO2, and those volumes of CO2 will have to be. You can't really use them in that sufficient quantity. You know, not. I mean, I didn't talk much about other utilization methodologies. You know, if there's so many people talking about making fuels, biofuels, and jet fuels from CO2. My problem with that is that to make a significant difference, first of all, you've got to use huge amounts of energy, so you need lots of renewables. And at the moment, we don't have enough renewable energy to be able to support a major fuel or whatever chemical utilization. And then when you've made the fuels and the chemicals, actually they're only semi-permanent capture. The fuels only last a few weeks before you burn and release the CO2 again. So, you know, those sorts of mass utilizations of CO2 are not really taking CO2 totally out of the atmosphere. And the only way to do that en masse is through carbon capture and storage.
Well, as I say,
we've just got to make it cheaper. And one of the ways of making it cheaper is by utilizing the CO2 in ways such as mineralisation and carbonation, where you can actually make value out of the CO2. And that I think is the main use of utilization technologies, is being able to sell a product that actually helps pay for the capture of the CO2 that you then pump underground, the rest of it.
But Paula, I think that raises an interesting question. When you say we've got to make it cheaper, if we don't make it cheaper, or if we just keep on going, the cost in the future is going to be horrendous. So it may well be worthwhile paying the cost now.
Oh, yes, yes. But it's going to have to be done with huge government subsidies. So that's the big question.
Well, I can only repeat, I thought what you said was absolutely correct. I just wish that other people would understand that as well as you seem to, and think it as obvious as you think it is.
Well, there's John here, so I have to say that, don't I?
You see, John, how everybody talks just to please you.
Not at all. No, I'm very much committed to CCS, but I still like to fly the flag for the EU, because I think it will help pay for the cost of the CCS.
Well, I mean, I think actually, at least in some frameworks, what you're doing will be called CCS, because, as I say, it's permanent storage.
Oh, yes, absolutely.
And you know, differentiate it from CCU, where it's used but it's released again.
Yes.
So you know, it's CCS by just another route.
Yes.
But you probably get more money if it's called CCUS. So go ahead and call it that.
I get depressed sometimes. So often am I putting the U into the CCUS, because there's a lot of publications on CCUS, but they don't mention the U.
Yes, yeah, no, that's good. I mean, it is good to utilize it, but I mean, from the climate's point of view, obviously the most important thing is the permanent storage, however you do that. doesn't matter.
Yeah, absolutely.
So we'll just have one more question, but then we really will have to stop. Radin, can you introduce yourself and ask the question, please?
Hello, hi. Actually, I'm using my son computer, so this is his name on the computer. My name is Mortaza.
Where are you from, please?
Paula, thank you very much for your very interesting presentation. Just a last question with regard to the previous, someone was called with regard to spreading, can you absorb the gas into a dry rock? And you mentioned, which is obvious, is you need to have some moisture in the rock. So is this means for hot countries like in Africa or Middle East, where there are lack of water or moisture because it's hot, it would be very doing the carbonate. It would be very difficult, or
no,
do it because it's very difficult to do it.
You don't need, well, especially particularly in a dry carbonation methodology, you don't need huge amounts of water, and you can effectively reclaim the water. So it is like using the water as a catalyst. It's not taking part in the reaction totally. So it doesn't require a huge amount of water. You do have to be careful about the temperature. The temperature control over the reaction is a very interesting area that we're working on. You know, what is the effect of higher temperatures? Mainly because of the solubility of the CO2. But we're using flue gas that is relatively moist. So there's always a lot of moisture in the flue gas itself, which helps in the reaction. So, I mean, we haven't done a lot of work in the Middle East and Africa yet, but I can't see any real barrier because it's not.
That would be actually because 2/3 of the development, as I understand, is required with regard to the carbon capture, is required in developing countries. So if we want to reach 2050 zero carbon emission, we need to do a lot of work in the developing country rather than in developed country, which is the US or Canada or Australia and Europe. Otherwise, we never reach 2050 because you know, they would go and use I mean, in Africa and Middle East would go for the cheapest energy, which is gas or oil, and so we never reach 2050. We need the water is very, very important over in countries in Middle East and Africa, and if we don't deal with the lack of water and infrastructure and the water treatment in those areas, are we going to get mass migration? And that is something I believe we need to deal with especially in Middle East.
I'm very passionate about sustainable building materials. So I think that the classic example is in India and around the Taj Mahal and Delhi, where there's huge amount of soil stripping, stripping of the topsoil to make bricks for the rapid construction and boom in urbanization. And you know, Al Gore's film of all those black smokers, making bricks, and that sort of building material is completely unsustainable. And there, I think carbonation and the use of waste materials to make construction materials in developing countries is a really important thing, and I'm quite passionate about it and would like the opportunity to be able to take our technology to developing countries for that reason. So not only are their fuel energy supplies unsustainable, but the construction materials are unsustainable as well.
Thank you very much. Thank you.
Okay. Well, and thank you very much, Paula. I think we really will have to stop there. But
Oh, thank you, John.
That's one of our more active sessions.
Oh, that's always nice. Good heavens, is it really that time as well? Goodness.
No, it really drags on. I mean, a lot of people had to leave, but a lot of people stayed on as well.
Yeah, well, that's very good. Thank you very much indeed for
thank you. It was great. Right, Karis, any official business before we close down?
So yeah, just to reiterate, thank you, Paula. That was really interesting and a very engaged Q&A and discussion afterwards, which is great. We'll have the lecture recording on our website next week as well for anyone who wants to kind of catch up or share the lecture as well. Just to let you know, for the other sessions that we have next week, we've got 2 sessions next week. On Tuesday, the 16th of February, we've got Professor Peter Cook from the University of Melbourne, who's giving us an update on CCUS developments in Australia, hence the 10 o'clock start for an Australian dial-in. And then on the Thursday, at our regular 2 till 3 slot, we've got CCUS updates from Germany from Dr. Dorothy Rebscher as well. So it'd be great to see as many of you that can make it next week as well. But yeah, thank you again today for Paula. That was really great.
Shall I send you over my presentation? Would that be useful to you?
That would be perfect. And we can pop that on our website as well.
Okay, lovely. Yeah. Okie doke.
Well, thank you.
Thank you. Very enjoyable. Thank you very much.